Alright, welcome back, Digital Electronics. Today we're going to cover some basic flip-flops and latches applications. Okay, so we're going to go over the D flip-flop and understand how it provides, timing for us. We've already kind of covered the D flip-flop a little bit. We're going to get in previous lectures, but we're going to get in more depth into it today. We're also going to talk about a JK flip-flop and the kind of the differences between the two, the JK flip-flop and the D flip-flop. And we're going to talk just slightly a little bit about what a transparent D latch is. Alright, and how we can use flip-flops to do control systems. Okay, so what are flip-flops? Flip-flops are really, how we control memory and what we can store into memory and how we call upon it and how we use it. Alright, so we're going to combine our combinational logic gates. Alright, we're going to have some inputs, and then we're going to have our memory from our flip-flop drive through that combo logic to produce our outputs. Essentially we're going to take like our date of birth project that we've done, and we're going to, make it automatic instead of us having to toggle through the switches and things like that. Alright, so this is a D flip-flop, and we're going to talk about the excitation table, right? How it works. Okay, so we have our clock in, alright, so that's going to be our clock, and this flip-flop works on the rising edge of the clock. So if you guys remember back from, first part of learning about signals and systems and things, where we talked about our square wave clock as it goes in, it had a rising edge, a falling edge, time high, time low, that sort of thing. So the rising edge of the clock is when we move through the D flip-flop. Alright, so Q will always follow D. Alright, so whatever D is, the next time through Q follows D. Alright, so we have Q and Q naught, or not Q. So if Q is 0, Q naught will be 1. If Q is 1, Q bar or Q naught will be 0. So that's what's going to happen on the rising edge of the flip-flop or the clock. Okay, so as the clock signal comes in, all right, we're going to translate through here. So if we look at the timing table here of the flip-flop, okay, Q will always follow D whenever we have the rising edge of the clock. Okay, so notice if we start from left to right, all right, we're going to start with Q at 0, we're going to start with D at 1. Then what happens? Okay, when the clock edge rises, so the rising clock edge is every dashed line that you see in this graph. All right, so when the clock rises to high, okay, Q follow D. So D is at 1, so what happens at the rising edge? Q goes to 1. Okay, and then Q follows D, but only on the rising edge. Notice that D drops down right away and drops down to low or 0, but Q stays at 1 until the next rising edge. So that second dash line, okay, if we take a look at it, that's what's going to constitute what's going on here. So if we're on all of these, okay, so I'm going to step back one time here so we can step through this. So Q will always follow D in every single scenario, but only on the rising edge. Okay, so that way we can kind of see through with this animation. So the arrows are showing that Q follows D only on the rising edge of the clock. It doesn't matter what happens between the clock edge. Okay, only when the rising edge of the clock hits, that's when Q follows D. So if you can just remember Q follows D on the rising edge, you will completely understand a D flip-flop. So that's how D's excite. Now let's talk about JK flip-flops. Okay, JK means we have two inputs. Our D flip-flop means we only have one input. We have D, that's our input. Okay, and when we have a JK flip-flop, we have two inputs. We have J and K. Okay, the outputs are going to be the same, Q and Q bar or Q and Q naught, and we will have the clock that comes in, and we are also going to do this on the rising edge. Now there are flip-flops where we can do the falling edge, okay, or we can pull data out to control it so it's on the falling edge as well. But this particular one we're going to talk about is for a rising edge. Okay, so what we have to do is we create a truth table here for the states of J and K. So when J and K are at 0, on the rising edge of the clock, there will be no change for Q. Q will be whatever it was previously. Okay, so 0, 0 does not change state for JK. Now, if we have a 0, 1, so if J is 0, K is 1, Q will be output to a 0. Okay, if J is 1 and K is 0, on the rising edge of the clock, Q will become a 1. And then when J is 1 and K is 1, we will toggle. Toggle means if Q was at 0, it will go to 1. If it was 1, it goes to 0. So it will toggle to the next state when we do a JK. All right. So if we look at them, okay, as we go through here, I'm going to stop back for a second and stay right here before I do the animation for you. If we look at J and K, okay, so right now J is at 1, K is at 0. So on the rising edge of the clock, all right, we can note that we have the state of 1, 0, which means Q will go to 1. Then if we look at the next state, J is at 1, K rises to 1 during that time, and at the rising edge we are at a 1, 1, which means Q will toggle. It was at 1, it's going to toggle down to 0. Okay? And then at the next rising edge, we have J is at 1, K is at 1. We will toggle again. So Q toggles, because J and K are both 1s, Q is going to toggle to 1. Then if we look at the next rising edge of the clock, all right, J drops down to 0, K is at 1. 0, 1 automatically tells Q to go to 0. It's not a toggle, it's using the truth table on the previous slide. Okay, and then at the next rising edge of the clock, you'll be able to see that J is at 0, K is at 0. So since it's a 0, 0 there at that rising edge, there is no change. Q remains at 0. Alright, so we'll let the animation kind of go through so that you can see how we get set, toggle, toggle, clear, no change, okay, and then back to set. Okay, so we can look at the different stages here based on the values of J and K as we toggle through. And it's really just based on that truth table. Okay, so, you know, if we have 1, 0, we're going to, if J is 1, K is 0, we're setting Q to 1. Okay, if J is 0, K is 1, we are clearing Q down to 0. If any time we are in a JK and both of them are 1, we will have a toggle situation. So you can look and see at the toggle situation. Anytime J and K are both 0, we will have a no change situation. Okay, so there's how we understand the timing of a JK flip-flop. Okay, so when we're talking about transition edges, okay, I keep talking about, you know, clock edges. We're talking about a positive transition edge, okay? Anytime the clock is going from 0 to 1, that's called a positive edge transition. Anytime we're going from 1 to 0, that's a negative edge transition. Okay, so that's going to help us when we get into counters a little bit later on, if we understand how to count up versus count down. We're going to get into that in a future lecture here, okay? But we can look at the way the excitation table happens here. If we have a rising edge clock or a falling edge clock, notice the difference. The positive edge trigger, notice what the schematic looks like for the D flip-flop. We have D, clock, Q, and Q bar. Notice the negative edge trigger, there is a bubble before the clock. Okay, so what are we doing? We're inverting the clock signal. So that's how we can make a negative edge trigger. So it'll come in with the opposite clock signal. And the signal will then change on the falling edge of the clock. So every time the clock goes from 1 to 0, we'll have the signal change there. We can do the exact same thing with the JK flip-flop. Okay? The normal one, the positive edge trigger, that's the schematic on top. The negative edge trigger for the JK flip-flop, okay, is we invert the clock signal. That's what the bubble means. We'll invert that input signal. Nothing changes with what's happening to the output. Notice the truth tables are the same for the JK, I'm going to step back, and the D right here. Okay, the outputs are still the same for JK and D. Okay, what changes is when those outputs occur. So the top one, okay, it's the example that we've already walked through, on the rising edge. Every time the clock hits the rising edge and going from 0 to 1, that's when we trigger the flip-flop. The only difference is if the negative edge trigger, we're only going to trigger the signal to change when we go from 1 to 0 on the clock. Okay, so we have our setup time and we have our hold time when we take a look at this. Okay, so TS, That's our setup time. That's how long we have before the clock triggers. Okay, so that's that distance. Even though, the input data here, D, or it could be JK, changes and rises, okay, it's not going to happen until the trigger on the clock rises. Okay, so that's our time setup. It's the time between when the data changes versus when we hit the positive edge clock. Okay, and then we have our hold time. That's how long we're going to hold until the next possible chance to change everything is. Okay, until the next clock transition. All right. Now we can make asynchronous inputs. So we've already done this a little bit in one lab, but what we can do is we can add a preset and a clear to this situation. So preset and clear are automatically going to make, preset is going to send the signal to 1, clear is going to send the signal to 0. Okay, so that's very, very important if we have a preset or a clear. And notice the states and when that happens. Notice that there's inverters on the preset and the clear. And that's the D flip-flops that we're going to be using in class, the 74 LS74s. Okay, they're both inverted there, so whenever we get the opposite signal. Okay, so if we have preset and clear, if those are both zeros, what are we going to actually do? It actually makes, Q go to 1. So you can look at the truth table here. So when we have a 1 and a 1 going into the preset and clear, essentially that's sending in a 0, 0 and sending it to 0. But we're inverting the signal there. Okay, so just as we go through. Notice we have an illegal condition there. An illegal condition is when Q is 1 and Q bar is 1. We can never have that occur. Alright, so we don't get to use that situation because they have to be inverted of each other. Alright, so if we look at a D flip-flop with preset and clear now, notice we still have dashed lines at the rising edge of the clock. In each scenario, we have the rising edge of the clock that we're going to follow. Q will still follow D, okay, unless we have preset or clear hit during the rising edge of the clock. Okay, so that's what's going to take place. So if we look at the first scenario, all right, see, preset's at 1, clear is at 1, D is at 1. All right, our clock is low. I'm starting on the left-hand side. We don't have a Q yet, right? But then we hit the rising edge of the clock. Q is going to follow D. Since D is at 1, Q will go to 1. Then if we look at the next rising edge of the clock, okay, nothing's happening with preset or clear when the clock is changing. So Q is going to follow D. Since D is at 0, Q will go to 0. Then look what happens. Before we get to the next rising edge of the clock, we hit the preset. Okay, we hit the preset. The preset button is hit. So Q automatically will jump up to 1. So these are the only conditions where Q does not follow D is when we have preset and clear. Anytime the preset button is hit on this flip-flop, Q will automatically go to 1 and stay at 1 as long as the preset button is hit. Okay, it won't change through the rising edge of the clock because preset will dominate what's going on to Q. All right, so whenever we let go of preset, then Q will go back to following D on the rising edge of the clock. Q will not instantaneously change and follow D until the rising edge of the clock. The only time Q will instantaneously change is if preset or clear is hit. Okay, so you notice the only time that clear is hit, what happened to Q? Okay, clear is only hit once in this graph, clear, when we go from 1 to 0. All right, whenever clear is hit, all right, Q will automatically go to 0. And then when we let go of clear, Q will get back onto the pattern of following D, but only on the rising edge of the clock. So it's very important that we maintain and keep track of what's going down. Okay, when preset triggers Q to go to 1. And then here we're getting clocked, and then we hit clear. Clear automatically sends Q to 0. Once we let go of clear, all right, Q follows D on the rising edge of the clock only. So you guys should be able to make these, draw these out for me and represent all these timing diagrams. If you can understand the timing of how the flip-flop works, it's really going to make sense when we do some of these calculations in class. All right, now we have a transparent latch. What do you see that's different on this one? Instead of a clock signal, we now have an enable signal. That's really the difference. So that means that we are going to manually, enable this and toggle between 0 and 1. Q will still follow D, but it's going to be based on when we enable. Okay? So that's really just the difference here. When we have a D latch, we have an enable instead of a clock that's automatically going to toggle through the states. Okay, so we have 0 when enable is not on, and we don't care what D is. D could be 1 or 0. We're going to have Q 0 and Q bar. Then if we switch the enable to 1, okay, and D is at 0, Q will be at 0, and Q bar will be at 1. Then if we have the enable at 1 and D goes to 1, Q follows D, alright, because that's how flip-flops work and store in memory. But this is how we use enable instead of a clock signal. So we have a latched signal, a transparent signal, a latched, a transparent, latched, transparent. So if we look at latched, what does that really mean? Well, latched means enable is at 0. Okay, so no matter what D is doing, we've latched Q into 0 because enable doesn't allow it to work. Then when enable goes to 1, once enable goes to 1, Q will follow D. So it's transparently, you can see that no matter what D is doing, Q is doing the same as D. Then if we turn enable off, okay, Q will stay in whatever state it was in when we turned the enable off. So Q stays in 1. It's latched into the 1 position. So regardless of what D does, when enable is not turned on, Q is going to stay in whatever that state was. Then we hit enable again. Okay, as soon as we hit enable, Q is going to follow whatever D does. So we can latch in whenever the enable is turned off. Q will always follow D when enable is turned on. Okay, and I'm saying off is a 0, 1 is an on. Okay, so if we look at flip-flop versus latch, okay, the main difference between the flip-flop and the latch is the latch has the enable and the flip-flop has the clock. Okay, so the clocks makes the flip-flop, the D flip-flop or the JK flip-flop, right? It's edge sensitive, so the flip-flop's going to work based on the edge of the clock, rising or falling. Okay, where the flip-flop with just that's with the flip-flop. With the latch, it's only going to work, all right, it's level sensitive. So if enable is 0 or enable is 1, okay, those are going to be the two different meanings. Okay, so that's really the difference between latch and flip-flop. Flip-flop, we have a clock that's going to automatically toggle through the signals. Okay, latch, we have enable, so you manually tell it when to turn on, when to turn off, and follow the signal. It's really the difference between the two. All right, so these are the chips we're going to use in class. We've already done the 74 LS74. We've breadboarded that in class and done some things. We're going to use that to drive your date of birth project. All right, so we're going to get through. We're going to do a lot here with mainly D stuff, and we're going to be breadboarding in class. But we might do a couple JK flip-flops as well. But these are the tags that you need to know. So if we have to breadboard, you have to pull up the data sheet on all of these. So the 74 LS74, okay, that's our flip-flop, our D flip-flop. The 74 LS76. Okay, that's our negative edge triggered JK flip-flop. So these are the chips that we have in class. And then we have the 74 LS75, that's the quad latch. Okay, so those are the flip-flops that we're going to use in class and breadboard. And then when you pull it up, right, we can look at the data table, all right, on the data sheet, and we can look at the connection diagram. Remember, the connection diagram is going to be very, very important for us when we breadboard these. So notice it's the same as all the other chips that we've done. VCC is pin 14, ground is pin 7, so that you guys need to make sure that you make up all the connections correctly when we're breadboarding this. Okay, so it's really just the same in the last couple slides for all these. This is what the JK flip-flop looks like, and these are all things that you're going to look up. Okay, notice now what's the difference. If we look back, I'm going to step back. The 74 LS74, okay, the D flip-flop only has 14 pins. If we look at the JK flip-flop, there's 2 flip-flops on there, but notice now there's 16 pins. So you got to be careful here which ones get VCC. All right, pin 13 gets ground, pin 5, gets VCC. So you have to be very careful when you breadboard with the JK flip-flop. You can't go off of memory like the D flip-flop. So this is one of the few ones. Okay, it's a 16-pin chip instead of a 14-pin chip. So if we do this one, you really have to pay attention to where you're putting ground and VCC. Okay, and lastly, if we take a look at the latch is also a 16-pin chip. VCC is 5, ground is 12. So we really got to be careful. Notice 13 is our enable here. So really making sure that when we use this, we have to follow the data sheets correctly when we breadboard these in class. Alright guys, well that's the end of the lecture. Let me know if you need to Zoom meet, team meet, or email me if you have any questions, or ask some questions in class. I'm probably going to go over a timing diagram again in class as well, so that we really nail this down. Okay? But guys, have a great day. I'll see you in class.